26,000 light-years away, at the exact center of our galaxy, something impossible is waiting. It is a point of no return, a place where space and time twist into shapes that human minds were never meant to comprehend. It has the mass of 4 million suns, compressed into a region smaller than our solar system. It has been there since the Milky Way was young, growing slowly, feeding on stars and gas and light itself. Every star you have ever seen in the night sky, every constellation, every familiar pattern, is orbiting this invisible giant. You are orbiting it right now, completing one lap around the galactic center every 230 million years. Tonight, we journey to the heart of our galaxy. Tonight, we fall into Sagittarius A star, the supermassive black hole at the center of everything we call home. If you find peace in these cosmic journeys, consider subscribing. Let us drift through the universe together, exploring the wonders that lie in the darkness between the stars. Close your eyes if you wish. Let the weight of the world fall away. Tonight, we are leaving Earth behind, leaving the sun behind, leaving everything familiar behind. We are traveling to a place that no human has ever seen with their own eyes, a place that remained hidden for centuries, a place that Einstein himself doubted could exist. The center of our galaxy is one of the most violent and beautiful regions in all of space. It is crowded with millions of stars, packed so densely that the night sky there would be ablaze with light. It is filled with clouds of gas and dust, sculpted by stellar winds and supernova explosions. And at the very heart of it all, surrounded by this cosmic chaos, sits Sagittarius A star, patient and eternal, bending space-time itself around its invisible form. For most of human history, we did not know it was there. The center of the galaxy is hidden from our view by vast clouds of dust that block visible light. We could see the band of the Milky Way stretching across the night sky, but we could not see what lay at its heart. It was only when we learned to see in radio waves and infrared light that the veil was lifted, and we glimpsed, for the first time, the monster at the center of our cosmic home. Let us begin our descent. The journey is long, but time moves differently among the stars. There is no need to rush. In the vastness of space, patience is the only virtue that matters. The story of Sagittarius A star begins with a mystery. In 1932, a young engineer named Carl Jansky was working for Bell Telephone Laboratories, trying to identify sources of static that interfered with radio communications. He built a strange antenna mounted on a rotating platform and listened to the sky. Among the crackles and hisses, he detected a faint but persistent signal, a whisper from the cosmos that rose and fell with the rotation of the Earth. Jansky traced the signal to a point in the constellation Sagittarius, toward the center of the Milky Way. He had accidentally discovered that the universe was broadcasting radio waves, that the sky was filled with invisible light that human eyes could never see. It was the birth of radio astronomy, and the first hint that something extraordinary lurked at the galactic center. Decades later, in the 1970s, astronomers identified a compact radio source at the exact center of the galaxy. They named it Sagittarius A star, the star notation indicating that it was the brightest radio source in the Sagittarius region. But it was not a star. The radio emissions were coming from something far more exotic, something that could generate enormous energy from a tiny region of space. The proof came from watching the stars. In the 1990s, two teams of astronomers began tracking stars near the galactic center, using infrared telescopes that could pierce the veil of dust. Year after year, they plotted the positions of these stars, watching them move against the background of more distant objects. What they found was astonishing. The stars were moving impossibly fast, some reaching speeds of thousands of kilometers per second, tracing elliptical orbits around an invisible point. One star, called S2, completed an entire orbit in just 16 years. At its closest approach, it passed within 17 light-hours of the galactic center, moving at nearly 3% the speed of light. The only object massive enough to hold a star in such a tight, fast orbit is a black hole. And from the orbits of these stars, astronomers could calculate its mass. 4 million times the mass of our Sun, compressed into a region no larger than our solar system. For this discovery, Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics in 2020. They had proven beyond doubt that a supermassive black hole sits at the heart of our galaxy, that the monster Einstein feared was real, that Sagittarius A star is one of the most extreme objects in the known universe. What is a black hole? To understand what awaits us at the center of the galaxy, we must first understand what a black hole truly is. The name itself can be misleading. A black hole is not a hole at all. It is not an absence of something. It is, in many ways, the ultimate presence. A concentration of mass and gravity so intense that it warps the very fabric of reality. Every object with mass bends space and time around it. The Earth bends space-time enough to hold the Moon in orbit. The Sun bends it enough to hold the planets. But these are gentle curves, subtle distortions in the cosmic fabric. A black hole bends space-time so severely that it creates a pit from which nothing can escape. Not matter, not light, not information of any kind. The boundary of this pit is called the event horizon. It is not a physical surface that you could touch. It is a mathematical boundary, a point of no return. Once you cross the event horizon, your future points inexorably inward, toward the center, toward the singularity. No force in the universe can push you back out. Even if you had an engine capable of infinite thrust, you could not escape. This is not because you lack the power to leave. It is because all possible paths, all possible futures, lead inward. Escaping a black hole is not difficult. It is impossible in the deepest sense of the word. At the very center of a black hole lies the singularity, a point where the equations of physics break down, where density becomes infinite, where our understanding of reality reaches its limit. What happens at the singularity is one of the greatest mysteries in science. General relativity predicts that space-time curves infinitely, that matter is crushed to infinite density. But infinity is a sign that our theories are incomplete, that something deeper is needed to describe what truly happens at the heart of a black hole. Sagittarius A star is a supermassive black hole, one of a class of giants that sit at the centers of most large galaxies. While stellar black holes form from the collapse of massive stars and typically contain 5 to 20 solar masses, supermassive black holes contain millions or billions of solar masses. How they form is still a mystery. Perhaps they grew from smaller black holes that merged over billions of years. Perhaps they formed directly from the collapse of massive gas clouds in the early universe. Perhaps they seeded from exotic objects that existed before the first stars. We do not know. They remain one of the great puzzles of modern astrophysics. Let us now begin our descent toward Sagittarius A star. We start from Earth, a small blue world orbiting an ordinary yellow star in the suburbs of the Milky Way. Our Sun is located about 26,000 light-years from the galactic center, roughly halfway out along one of the galaxy's spiral arms. From here, the center of the galaxy is invisible to our eyes, hidden behind vast clouds of gas and dust that scatter and absorb visible light. But we will travel in our imagination, beyond the limits of light and time. Let the cosmos carry you. Feel the familiar pull of Earth's gravity fade as we leave our world behind. The sun shrinks to a bright point, then to one star among many. The constellations distort and dissolve as our perspective shifts. The familiar sky of Earth gives way to the endless sea of the galaxy. We are traveling inward now, toward the core of the Milky Way. Around us, the density of stars begins to increase. In the spiral arms where Earth resides, stars are scattered relatively far apart, separated by light-years of empty space. But as we approach the galactic center, the stars grow more numerous, more crowded, more brilliant. The sky fills with points of light until the darkness itself seems to glow. We pass through clouds of gas and dust, the raw material of stars. These clouds glow in infrared light, heated by the stars embedded within them. New stars are being born here, blazing into existence from the collapse of cosmic gas. Old stars are dying here, shedding their outer layers into space, enriching the galaxy with heavy elements forged in their cores. The cycle of stellar life and death continues all around us, indifferent to our passage. As we travel deeper, the environment grows more extreme. The stars are older here, many of them red giants, bloated with age. Others white dwarfs, slowly cooling into darkness. The gravitational pull of the galactic center has shaped this region for billions of years, stirring the stars into complex orbits, occasionally flinging one out into the halo, or sending another spiraling inward toward the black hole. And then, ahead of us, we see it. Not the black hole itself, for a black hole emits no light, but we see its influence, its presence, written in the motion of the stars and the glow of superheated gas. We see the galactic center, the heart of the Milky Way, the region where Sagittarius A star waits. The galactic center is a realm of extremes. Within the central few light-years, there are millions of stars, packed so densely that collisions between stars are not uncommon over cosmic timescales. The average distance between stars here is only a few light weeks, 1,000 times closer than stars in our neighborhood. If Earth orbited a star in this region, the night sky would be magnificent, a blaze of light with no true darkness anywhere. But this region is also dangerous. The intense gravitational field of the black hole perturbs stellar orbits, sending stars on chaotic paths that can bring them dangerously close to Sagittarius A star. Tidal forces can tear stars apart, stretching them into long streams of gas that spiral inward and feed the black hole. When this happens, the material heats to millions of degrees and releases intense bursts of radiation. We call these events tidal disruption events, and they are among the most violent phenomena in the universe. Around Sagittarius A star, there is a structure of young, massive stars that astronomers call the stellar disk. These stars are only a few million years old, babies by cosmic standards, and they orbit the black hole in a flat, disk-like configuration. How they formed so close to such a destructive object is a mystery. Stars should not be able to form in the intense tidal environment near a supermassive black hole. And yet, there they are, defying our expectations, orbiting the monster that should have destroyed them at birth. Beyond the stellar disk lies a structure called the circumnuclear disk, a ring of gas and dust about 5 light-years across. This disk is tilted and warped, shaped by the complex gravitational environment of the galactic center. It contains enough material to form 1 million stars, and it feeds a slow trickle of gas inward toward Sagittarius A star. This gas will eventually fall into the black hole, adding to its mass, contributing to its slow growth over cosmic time. As matter falls toward a black hole, it does not simply drop straight in. Conservation of angular momentum causes the material to spiral inward, forming a flattened disk of superheated gas called an accretion disk. This disk is one of the most extreme environments in the universe, a place where matter is heated to billions of degrees, where magnetic fields twist and writhe, where physics operates at its most violent edge. In the accretion disk, friction between layers of gas moving at different speeds converts orbital energy into heat. The inner parts of the disk, closest to the black hole, glow with X-rays, their temperatures reaching hundreds of millions of degrees. Further out, the disk cools to mere millions of degrees, glowing in ultraviolet and visible light. The accretion disk can outshine entire galaxies, releasing more energy than 1 trillion stars. Sagittarius A star, however, is currently quiet. Its accretion disk is thin and faint, starved of fuel. Compared to the supermassive black holes in active galaxies, our black hole is nearly dormant, accreting only a tiny trickle of material. Astronomers estimate that Sagittarius A star consumes less than the equivalent of 1 Earth mass per year, a modest diet for a 4 million solar mass monster. But it was not always so quiet. Evidence suggests that Sagittarius A star was far more active in the past, perhaps millions or billions of years ago, when more material was available to feed its hunger. The giant bubbles of gas extending above and below the galactic plane, discovered by the Fermi Gamma Ray Space Telescope and called the Fermi bubbles, may be relics of ancient outbursts, explosions of energy released when the black hole feasted on vast quantities of gas. Our black hole remembers its violent youth, and as we approach the accretion disk, we must be cautious. The radiation here is intense, the magnetic fields chaotic, the temperatures lethal. But in our cosmic journey, we pass through unharmed, observers from outside time, witnesses to the spectacle of matter's final dance before it crosses the event horizon and vanishes from the universe forever. We are close now, closer than any star has ever approached without being torn apart. Before us lies the event horizon of Sagittarius A star, the boundary between the universe and the unknowable. The event horizon of a 4 million solar mass black hole is surprisingly large. It has a radius of about 12 million kilometers, roughly 17 times the radius of the Sun. If you placed Sagittarius A star at the center of our solar system, its event horizon would extend about 1/10 of the way to Mercury. For a black hole, this is vast. For a region containing 4 million solar masses, it is impossibly small. From a distance, the event horizon appears as a perfect sphere of darkness, outlined by the glow of superheated gas behind it. Light from the accretion disk bends around the black hole, creating a bright ring that astronomers call the photon sphere. Photons in this region can orbit the black hole, circling around and around, before eventually spiraling in or escaping to infinity. The photon sphere marks the boundary where light itself is trapped in orbit around gravity. In 2022, the Event Horizon Telescope captured the first image of Sagittarius A star. Using a network of radio telescopes spanning the globe, effectively creating an Earth-sized telescope, astronomers resolved the shadow of our black hole against the glowing ring of accreting gas. The image confirmed what theory had predicted: a dark circle surrounded by a bright, asymmetric ring, the telltale signature of a supermassive black hole. For the first time in human history, we had seen the shadow of the monster at the heart of our galaxy. The event horizon is not a physical surface. There is no barrier you would feel if you crossed it, no wall or membrane marking the boundary. If you fell into Sagittarius A star, you would not notice the exact moment you crossed the event horizon. You would simply notice, if you looked back, that the universe outside had begun to change, that the stars were shifting and dimming, that your connection to the outside cosmos was fading. And then, gradually, you would realize that there was no going back, that all paths led inward, that you were falling toward the singularity with no hope of escape. Let us cross the threshold. Let us fall into Sagittarius A star and see what lies beyond the event horizon. As you fall, something strange happens to your perception of time. From your point of view, time passes normally. Your watch ticks at its usual rate, your heart beats steadily. But to an observer watching from a safe distance, your fall appears to slow down. As you approach the event horizon, you seem to move more and more slowly, your image stretching and reddening as the photons you emit struggle against the pull of gravity. From the outside, you would appear to freeze at the event horizon, never quite crossing it, fading slowly into darkness over billions of years. But from your perspective, you cross the event horizon in moments. Inside, the nature of space and time shifts. Outside the event horizon, you could, in principle, move in any direction, forward or backward, left or right. Inside, the radial direction becomes time-like. Just as you cannot avoid moving forward in time outside a black hole, you cannot avoid moving inward in space inside one. The singularity is no longer a place in space. It is a moment in your future, inevitable and inescapable. Because Sagittarius A star is so massive, the tidal forces at the event horizon are relatively gentle. For a stellar mass black hole, the difference in gravitational pull between your head and your feet would tear you apart long before you reach the event horizon. stretching you into a thin stream of atoms in a process called spaghettification. But for a supermassive black hole, the event horizon is so large that the tidal gradient is more gradual. You could cross the event horizon of Sagittarius A star intact, body and mind whole, aware and conscious as you fall towards your ultimate fate. Inside the event horizon, the darkness is absolute. No light from the outside universe can reach you. You fall through a void more complete than any space between the stars, a darkness unbroken by any photon, any glow, any hint of the cosmos you left behind. This is the true darkness, the absence of all light, the silence of space-time folded in upon itself. Time becomes strange inside the black hole. From your perspective, you have perhaps minutes or hours before you reach the singularity, depending on where you crossed the event horizon. You fall through emptiness, weightless in the truest sense, following the curve of space-time toward its ultimate conclusion. As you fall deeper, the tidal forces begin to grow. Even for a supermassive black hole, the singularity is a point of infinite curvature, and the gradient of gravity increases as you approach. Your body begins to stretch, subtly at first, then more noticeably. The difference in gravitational pull between your head and your feet grows larger with each passing moment. If you could look around, you might see strange things. The geometry of space-time inside a black hole is unlike anything in ordinary experience. Photons follow paths that loop and curve in unexpected ways. Light that should travel in straight lines bends and twists, creating optical illusions that confound normal perception. Some physicists have speculated about what you might see as you fall. Distorted images of yourself, light trapped in orbits around you, views of possible futures flickering at the edge of perception. But there is no escaping what comes next. The tidal forces grow stronger, stretching your body along the radial direction, compressing it along the perpendicular axes. This is spaghettification, the same process that tears apart stars that venture too close to black holes. For you, it begins gently, but it accelerates relentlessly. Within minutes, your body would be stretched beyond recognition, pulled into a thin thread of matter, falling toward the singularity. At the center of Sagittarius A star lies the singularity. It is the endpoint of all paths inside the event horizon, the final destination of everything that falls in. According to general relativity, the singularity is a point of infinite density, a place where space-time curvature becomes infinite, where the known laws of physics break down completely. What happens at the singularity is perhaps the greatest mystery in all of physics. Our theories simply stop working. General relativity, which so beautifully describes gravity as the curvature of space-time, predicts its own demise at the singularity. The equations produce infinities, mathematical singularities that signal the breakdown of the theory. To understand what truly happens at the center of a black hole, we need a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics. We do not yet have such a theory. Some physicists speculate that the singularity is not a point, but a ring, a circular structure through which you might pass to emerge in another region of space-time. This is the basis of many science fiction tales involving black holes as portals to other universes or distant parts of our own cosmos. But these solutions to Einstein's equations assume perfect symmetry and the absence of any matter falling in. In reality, Black holes are formed from collapsing stars and fed by infalling matter, and the singularity is likely far more complex and chaotic than these idealized models suggest. Others propose that quantum effects become important near the singularity, smearing out the infinite density into something finite but incomprehensibly extreme. Perhaps the singularity is a region where space and time themselves break down, where the concepts of location and duration lose their meaning, where reality, as we understand it, simply ends. We may never know for certain. The singularity is hidden behind the event horizon, forever shielded from observation. No information can escape to tell us what happens there. The interior of a black hole is the ultimate secret, locked away from the universe by the laws of physics themselves. Time and the black hole. One of the most profound effects of a black hole is its influence on time. According to general relativity, gravity slows time. The stronger the gravitational field, the slower time passes. This effect, called gravitational time dilation, has been measured on Earth and in the solar system. Clocks on satellites run slightly faster than clocks on the ground. Time passes more slowly at the surface of the Sun than it does on Earth. Near a black hole, this effect becomes extreme. At the event horizon, time slows to a stop from the perspective of an outside observer. If you watched someone fall into a black hole, you would see them slow down as they approached the event horizon, their movements becoming sluggish, their light becoming redder and dimmer. They would appear to freeze at the edge of the black hole, never quite falling in, fading slowly into darkness. From the perspective of the person falling, however, time passes normally. They cross the event horizon in an instant and continue falling toward the singularity. The asymmetry between these perspectives is one of the strangest aspects of black hole physics. Two observers experience completely different realities, and both are equally valid. Inside the event horizon, time and space swap their roles in a certain mathematical sense. The radial coordinate, which describes distance from the singularity, becomes time-like, while the time coordinate becomes space-like. This is a profound and disorienting transformation. Just as you cannot avoid moving forward in time in normal space, you cannot avoid moving toward the singularity inside a black hole. The singularity is not a place you can avoid. It is a moment in your future, as inevitable as tomorrow. Around Sagittarius A star, a family of stars performs an endless cosmic dance. These are the S stars, a group of young, massive stars that orbit the black hole on highly elliptical paths, swinging close to the event horizon before retreating to safer distances. The most famous of these stars is S2, a blue giant about 15 times the mass of the Sun. S2 completes one orbit around Sagittarius A star every 16 years, reaching speeds of up to 25 million kilometers per hour at its closest approach. When S2 passed closest to the black hole in 2018, astronomers detected the gravitational redshift of its light, a direct confirmation of Einstein's general theory of relativity. Even more extreme is S4714, a star that approaches within just 6 billion kilometers of the event horizon, closer than Neptune orbits the Sun. At its closest approach, this star is moving at more than 8,000 kilometers per second, about 2.5% of the speed of light. The tidal forces on S4714 must be immense, stretching the star's atmosphere into strange shapes as it whips around the black hole. These stars are living laboratories for testing the predictions of general relativity. By carefully tracking their orbits, astronomers can measure the precession of their orbital paths, the time dilation of their light, and the subtle frame dragging caused by the spinning black hole. So far, Einstein's theory has passed every test with flying colors. But the S-stars may eventually reveal the limits of our current understanding, showing us where general relativity breaks down and where new physics is needed. How these stars came to be in such extreme orbits is still a mystery. They are young, only a few million years old, yet they orbit in a region where star formation should be impossible. Perhaps they were captured from binary systems that ventured too close to the black hole. Perhaps they formed in a disk of gas orbiting the black hole and migrated inward over time. The S-stars are a reminder that the galactic center still holds many secrets. The future of Sagittarius A star. Sagittarius A star has been at the center of our galaxy for billions of years, and it will remain there for billions more. But its future is not one of eternal stasis. The black hole will continue to grow, feeding on gas and dust and the occasional unfortunate star. Over cosmic timescales, it will consume more and more of the galactic center, growing ever more massive. In about 4.5 billion years, something dramatic will happen. The Andromeda Galaxy, our nearest large neighbor, is currently approaching the Milky Way at about 400 kilometers per second. Eventually, the two galaxies will collide and merge, their stars intermingling, their structures transforming into something new. And at the centers of both galaxies, supermassive black holes will approach each other. The supermassive black hole at the center of Andromeda is even larger than Sagittarius A star, containing perhaps 200 million solar masses. When the galaxies merge, these two black holes will spiral toward each other, their orbits decaying as they release energy in the form of gravitational waves. Eventually, they will merge